A very good morning to the subscribers and viewers of DRCOA All Slot 2020 students, and I'd like to thank Dhanabal sir for giving me this opportunity to present on the topic performance analysis of single precision floating point MAC for deep learning. This was studied and detailedly analyzed from a IEEE research paper, and let's start with how is this related to computer organization and architecture syllabus. As you know, an FPU is a micro math coprocessor which is used for fast analyzation of data, which was recently released in Intel Pentium and Motorola 6800 series, and then the trend has been changed. And as we know, floating point unit is a basic model in our syllabus, and I want to enhance its performance and show how a floating point is very important in organization and architecture. Now let us look into some diagrams existing architectures of the problem statement that I just stated of deep learning, and this is the diagram, a block diagram which is provided in the research paper, which I analyzed completely, and I have drawn this diagram in draw.io as you are seeing it right now, where you have a multiplier and a multiplicand, where it's being multiplied in the multiplier logic unit, and it's being sent to the adder, which is then stored in the accumulator, and the final output is again moved to the adder. Moving on with our topic. So these are the partial products which are produced in this FPUs. FPUs, as I told you, in deep learning, you see the 0, 0, 0 has a partial product of 0, and when you initialize a different address, that is when from I plus 1 you move it to I minus 1, you get a different result, and these 0, 0, 0 are nothing but binary numbers, and which provides a unique partial product. And you would be wondering what MAC is. MAC has few operations as you see here, and which shows how much power does each operation have in itself. Add and shift has 225.76 microwatt, and it takes up an area of 36,921.14 micrometer square. Similarly, you see the total power and the delay which is being taken into consideration. And as you saw here, the detailed analysis and graph of that is being telecasted in this page. Further moving down, and when you differentiate the distance in nanometer, for 45 nanometer, you see a significant reduce in the power that is consumed in all the cases. Similarly, in this diagram, the area is considerably reduced by 1/8 of its, or say 1/7 of its proportion. Now, the proposed architecture, as we saw before, a similar architecture with few technical specifications into it for better understanding and better learning of the topic that I have chosen. And this is the diagram that I have constructed in draw.io, and this just is the same architectural design in depth as shown in here. If you're able to see this, This is the same diagram. These blocks have different port numbers as you see on the screen, and which is being connected, and finally all the values have been stored in the register. Further adding to the content, this is the matrix form of the diagram that you just saw above here, because our question states that draw the proposed architecture as discussed in the paper using vector graphics application software, which is being used here. Now let us see what is the existing architectures that is being present and the architecture that I have proposed right now. As you see, using floating point representation for ways is more efficient, as you have the variable term and it doesn't have to be in a fixed range, and the experimental results that has been come up is for weight storage is up by 36%, and the power consumption of the hardware is up by 50%. The hardware that I have proposed has less depth than conventional floating point MAC and achieved a lower area requirement other than floating point MAC implementations. Continuing our discussion with advantages proposed for the design that I have given, in which you see that the 4x2 adder, the power consumed is reduced by 60%, and the MOS transistors are also reduced by 28%, which reduces the complexity of the entire diagram. And this is all a few examples and statements which were provided and analyzed. And the multiplication speed was 67 faster than the existing Wallace tree. Wallace tree is another specification which was 53%, and also faster than Vedic multiplier, and 22% faster than Radix 8-booth multiplier. And you can see all the benchmarks given in this page. Now moving on with the merits and demerits. As I told before, the speed of the multiplier in the proposed design is significantly faster than all the booth multipliers which were already proposed in the previous generations. But the problems, which are the demerits, are it has an increased gate count, and the power and area are significantly larger. Now let's come to the generalized topic of applications of the proposed design. As you know, in deep neural networks, in artificial intelligence, in machine learning, this all can be utilizing my proposed design, and will be able to also be helpful in imaging of cancer, survival prediction, big data analytics, and also in unmanned aerial vehicles, which is used for deep learning. So, taking all this into consideration, this might be a good future proposed design and will be helpful in various sectors in our industry. And I would like to thank all of you for patiently listening to my presentation.